Now that we've talked about subatomic particles and isotopes, we're going to talk about atomic weight. Atomic weight is the average atomic mass that is given on the periodic table. So we're going to use the same table that we looked at earlier that compared the isotopes of carbon. We're going to use that to talk about average atomic mass, or the atomic weight that you see on the periodic table. So average atomic mass, it isn't simply an average of, three numbers like you're used to thinking about if you were going to average, your exam, your class average for an exam or something. It's not just the total, you add them all up and you divide by the total number. The average atomic mass is weighted based on the abundance on Earth. And so what it means is that if you walked out into the world and you found a gazillion carbon atoms and you brought them back to the lab and you measured the mass on a scale, you divided by the gazillion atoms you had, it would represent the average mass of one atom. So these masses are weighted based on their abundance on this planet. If we were on a different planet, it would have a different abundance and a different average mass. So that word average is misleading, okay? It's weighted based on relative abundances. You need to know the relative abundance in order to do this calculation. Those are given in the table. That's what these numbers represent. So the average atomic mass for carbon, we're going to take our 98.9% and we're going to turn that into a relative number out of 1 fraction. And then we're going to add in the other isotope that has reasonable abundance, which is carbon-13. And we get these two numbers. Now, if we're figuring out significant figures, the 12 is exact. It's the only exact number on the table, okay? It's the only exact number for the elements that we know. That 12 is exact, which means that the 11.868 is accurate to that first 8. It has 3 sig figs because the 0.989 has 3 sig figs. The second number, 0.143036903, is accurate to the 4 because of the 0.011. That number only has 2 significant digits. So even though the 13.0033548378 has a bajillion significant digits, it doesn't matter because the 0.011 only has 2. So now when we get our final answer, that first step involved multiplication, but our last step involves addition. So when we add those two numbers together, we get 12.0110369. That first number, 11.868, is accurate to the 10th place. The second number is accurate to the 100th place, which means that your answer is only accurate to the 10th place, which means that we're going to round it to 12.0 AMU. And that is our answer. Put a little box around it. Now we're going to do a calculation just to make sure everybody knows how to do this on their own. So atomic mass versus average atomic mass. Let's talk a little bit more about that. So this little pie chart represents the abundances on Earth of magnesium's 3 naturally occurring isotopes, magnesium's 24, 25, and 26. You can see the same information in the table below. So the most abundant isotope is magnesium 24. Now, these numbers here represent the atomic mass of each isotope of magnesium. So when somebody says atomic mass, that is the actual mass of a given isotope of a given atom in atomic mass units. That is not the same thing as the average atomic mass or the atomic weight that you see on the periodic table. So if we were going to calculate the average atomic mass for magnesium, we would do this calculation, where you have each abundance, 0.789, so that's the 78.9%, and we have made it a fraction out of 1 instead of out of 100. And again, you can make it 78.9 divided by 100 as a fraction, but that's the same as 0.789. And then you multiply that number by its mass, which is also given in the table, and then you add to that the next one, which is 10% abundant, 0.100 times the next mass, and then 0.111 which is 11.1% times its mass. Now, as we figure this out, it's easiest for significant figures to do each calculation separately. So this first part, 0.789 times 23.98505, is 18.924. And the 0.1 times 24.98584 is 2.48498584. And then the third part, 0.111 times 25.9826 is 2.884066. I wrote those in gray. It's a good idea to write down the individual numbers, only because later when we're figuring out significant figures, it's easiest if you have those intermediate numbers written down. So the answer ultimately is 24.3068575. But if we want to round to the correct number of significant digits, we have to go through each step in that calculation and figure out how many it should have. So in the first part, 0.789 times 23.98505, 0.789 has 3 significant digits, and then the other number has a lot more than 3, but the 18.9 is accurate to the 9. The second part of that calculation, 0.100, has 3 sig figs, and so the answer to that product is 2.49. It's accurate to the 9, which has 3 sig figs. The third part of that calculation, 0.111, has 3 sig figs, and 25.9826 has 6. But that product is only accurate to 3 sig figs, so 2.88. So when you add those numbers together, this last step, we're summing these numbers. We're summing 18.9, 2.498, blah, 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 2.88406686. We're adding those three numbers together to get this final sum. Now the addition rule says that this first number, 18.924, is only accurate to the tenths place. The second number is accurate to the hundredths place, and the third number is accurate to the hundredths place. So that means that my answer is only accurate to the tenths place. So 24.3 atomic mass units for the average mass of magnesium. We're going to do one more example. We have lead, which has 4 naturally occurring isotopes. You can see the pie graph. Lead-208 is the most abundant isotope. So you can make a prediction that lead-208, that the average mass will be closer to 208 than it is to the others. So we're going to do our calculation. The atomic weight is 0.014, that's the 1.4% for lead-204. This is its actual atomic mass, and that goes here. 24.1 is the same as 0.241 out of 1, and then multiplied by its mass, and then 0.221 will go here times its mass. 0.524 will go here, and then this mass didn't quite fit in there, so it goes there. You end up with these intermediate numbers. And we can go ahead and finish the calculation and then figure out significant figures at the end. But remember, I like to write down the intermediate numbers so that sig figs are easier to calculate. So let's go ahead and figure out sig figs. The 0.014 has 2, 203.973 has 6. So this intermediate product here, 2.8, is only accurate to 1 sig fig, or I mean, sorry, to 1 digit after the decimal, 2 sig figs because of the 0.014. This second set, 0.241 has 3, 205.9745 has 1, 2, 3, 4, 7. That's a lot of sig figs. And so this number, 3 sig figs, 7 sig figs means 3. 0.221 has 3. This has a lot, so this has 3. This has 3. This has a lot, which means this one's accurate to 3. Now, the last step is we're adding these 4 numbers together. So the sum of those 4 numbers is this number at the bottom, our final answer. But remember, the addition-subtraction rule says that the final answer can't be any more accurate in terms of its place value than the least accurate number. 2.8 is accurate to the tenths place. This one's accurate to the tenths place. The 7 is in the tenths place. This 8 is in the ones place. And so that means our final answer is only accurate to the ones place. And so when we finally write our answer down, it's going to be 207 because that 2 rounds down. This is our last bit of practice for atomic weight. So I might ask you to calculate an average mass or an atomic weight, but I might ask you other questions that are related to atomic weight. So let's make sure we know how to do all the different kinds of questions. So number 3 here, europium, element 63, has 2 isotopes. Which of the following statements must be true? This is a multiple choice question. Now remember that you have a periodic table. So element 63, europium, is here. Okay, so what's relevant about this is that europium's atomic weight is 152 AMU. So we're going to write that down on the next page. 152.0 atomic mass units is the average atomic mass or atomic weight. That's important because europium 151, that specific isotope, probably has a mass of about 151 AMU, and europium 153 is going to have a mass of about 153 AMU. But 152 is kind of right in the middle of those two, which means that the two isotopes are probably, or are definitely, very similar in abundance, okay? So C is definitely the answer here, and I don't know if you can see that each of these isotopes is weighted equally in the average, okay? So C is the answer, but let's talk about answers A and B just to rule them out, make sure everybody understands why they're not right. So answer A, europium 151, is much more abundant than europium 153. If that were true, then the average mass on the table would be much closer to 151 than it was to 153 because that number would be weighted more heavily. So we know that that's not true because the average mass is 152. If B were true, then the average mass would be much closer to 153, but it isn't, and so we know B is also false. So C must be the answer because 152 is halfway between 151 and 153, which means that they're about 50-50 in abundance. Let's move on to number 4. So we have an element antimony has an atomic weight of 121.757 AMU. It only has 2 naturally occurring isotopes. One isotope has an abundance of 57.30% and isotopic mass of 120.904 AMU. Based on these data, what is the mass of the other isotope? Now, this is related to the problems you did before, and you're going to use the same equation you used before in order to determine the answer. But you have to sort of set it up algebraically. Okay, so let's talk about how you're going to set it up. One thing that you know from the periodic table, which you're going to have, is the average mass. Now, you're given an atomic weight here, and you have your formula here for average mass. So the abundance is here, and we know the abundance of the other isotope is 42.70. And the reason we know that is because that we know there are only 2 naturally occurring isotopes, which means that those 2 must add up to 100% abundant, which means we can calculate the abundance of the second isotope. And that's a step that might confuse you. So if it only has 2 isotopes, you know you can calculate the abundance of the second one. So we'll plug in the mass for the first isotope. We'll plug in the average mass, which is 121.757. And then the mass of the other isotope, that's what we're looking for. And that is in the formula here at the end. And we're just going to set that equal to x, and we're going to solve algebraically for it. So we're going to plug it in as an algebra expression, and we're just going to solve for x. So this is my first part of the answer. And then when I want to solve for x, ultimately, I'm going to get this expression. Then I'm going to do this division step, and I will get an answer, which is here. Now the last step is going to be to figure out how many significant figures should be in this answer. So in order to do that, you kind of have to go through step by step. It's a bit tedious, but we're going to start with our first calculation, which is here, the 0.5730 times 120.904. This number has 4 sig figs. This number has 6 sig figs, which means that my first answer, the 69.277, should have 4, right? And so it's accurate to here. And then the second part of my calculation is this 121.757, and we're going to subtract this 69.277. And that means that we are, that the subtraction step here, the difference we get, 52.479, is accurate to the hundredths place, because this 7 is the thousandths place, and this 7 is the hundredths place. So my answer here, my intermediate answer here, is accurate to this 7. Now the final step is a division step where we have 4 sig figs and we're dividing by 4 sig figs. This 0.4270 comes from up here. This number is accurate all the way to this 0 because this 100% in the abundance is an exact number, and we're subtracting 57.30, which is accurate to the hundredths place. So this number has 4 sig figs, which means 4 divided by 4 means our answer should have 4, which means it's accurate to that 9. So 122.9 atomic mass units. Now the last problem, the most abundant element of cesium has a mass of 132.9054 AMU. Now, if we look at cesium here, 132.9, this periodic table isn't really very accurate. And so if we use a different periodic table, so this is a periodic table I got from the internet, and you can see here 132.9054 AMU. That is the average mass on the table. So if we go back to here, what this is telling us is that the mass of this isotope of cesium is the same exact number as the average mass on the table. So what that means for us is that this is the only isotope of cesium that exists on Earth. And therefore, when we answer question part A, we can say that the abundance of this isotope is 100%. And that's because the periodic table mass matches the mass of this isotope. Now let's look at problem B. Problem B is asking about how many neutrons are present. If we take our mass of this particular isotope, 132.9, we round it to the nearest one integer. That's 133. That's the mass number of this isotope, is cesium-133. So that is the number of protons plus neutrons. All we have to do is subtract away the number of protons, and we will have the number of neutrons. So we'll go back to the table, and we'll look at the number of protons. That's here, 55. 55 protons. And then we'll come back and we'll subtract that number from 133. 133 minus 55 is 78. 78 neutrons is my answer.